Let's see, this is page 37. So if this series converges, we know there's a hidden zero there, right? So we know that the series will always converge at its center. We know the center is at 0. It does converge for -8, so the radius is going to be at least -8, right? So we know that our radius of convergence is going to be x minus c. It's at least going to be this, right? Which means that it's going to be between -8 and 8. Okay, so it says converges here. We don't know if it converges at 8. But if we know that our interval is between -8 and 8, we can safely say that -6 will converge. But 8 is kind of a we're unsure about that, so we can say for sure 0 is -6. That makes sense. Okay, so today we're talking about a little bit more about error bounds. But now we're talking about error bound. What if we're dealing with power series that don't have alternating signs? Okay, so without alternating signs, we can still find the error, but it's going to be similar, but then it's also going to be a little bit more involved. So let's go to page. Yeah, page 41. Okay, so again, we know what error bound is. Error bound just means how far off is a safe maximum error for how far off our approximation is from the actual value. And we saw with alternating series bound that if we want to find, if it's an alternating series and if the alternating series guarantees to converge, then we know that a safe upper bound for a partial sum is just to look at the first unused term, right? The first unused term is not going to be the exact error, but it will give us an idea that we know our approximation is not going to be off by no more than the first unused term. So that's a very convenient way to get to how accurate our partial sum is. So we're still going to take this idea that we did with alternating series error bound. It's just that now, what if we have a series that is not an alternating series? We're still going to be involving the first unused term. So we know this is true, right? The exact value is going to be some Taylor polynomial plus some remainder, right? And obviously, our Taylor polynomial, the better, the more terms we use, the more the smaller our remainder will be. Okay, and that Taylor polynomial will just be at some, some nth term, right? It could be the first few terms added together. It could be the third degree polynomial. It could be the fifth degree polynomial. Okay, but we know that in general, this is true. So if I were to just basically solve for my remainder will just be what minus what? Yeah, just whatever the exact value is minus my approximation, that's going to be my remainder. Right, really, we're just, so we call the remainder the error. Okay, so the nth term remainder is going to be equal to whatever the exact value is minus my polynomial degree, Taylor polynomial of the nth degree. Really, but we're just rearranging the equation. It looks complicated, but we're just saying the remainder is just whatever is different between the exact and the approximation. Okay, so let's say we want to do an approximation of a function, right? And we can start building our Taylor polynomial f of c plus f prime of c x minus c, right? We start off with first order degree, and then the second, third order, they follow a very specific pattern. Second derivative of c over 2 factorial times x minus 2 factorial, 2 minus x minus c squared. And we just keep going until we get to our nth Taylor polynomial. And we know that whatever that nth Taylor polynomial, if it is a value that that ends, right? Could be the 100th, could be the 200th, could be the 5th. We know that that there's going to be some remainder, right? Unless we go out to infinity, there's always going to be some remainder. Okay. So the remainder is going to be involving the first unused term. So it's going to be the n plus first derivative evaluated at c for x minus c to the n plus 1 over n plus 1 factorial. That's how we've been usually, we kind of imagine this is going to be how we're going to approach something for an alternating series, right? We should look at the first unused term. But what's different is because of the fact that this is no longer a alternating series, we have to do a slight adjustment. And that slight adjustment is that we need to find the n plus first term evaluated at some unknown x value, which we're going to call z. So this is going to be the actual remainder. But the problem is that we're not going to be able to know what that z is, because if we knew what that z was, then there will be no need for a remainder, right? If we knew what the exact error was, then there will be no need for error bound. So what we want to do is we want to be able to find out what is the maximum value of the n plus first derivative between my x value and my center. As soon as I can find out what that value is, then I can find my error bound. So the only difference that we have from alternating series error bound, before we just find the n plus first derivative. Now we have to find the n plus first derivative and do a little bit of adjusting and see, okay, what is the maximum value that can come out of this? And we only have to do two things to test what that maximum value is. we call this the Lagrange error bound. I think sometimes I'm hard to pronounce Lagrange. I'm going to say Lagrange. So it says let f of x be the differentiable through the order n+1. The error between the Taylor polynomial and the function is bounded by, so the nth degree remainder is guaranteed to be less than. Okay, so we're gonna maximize, find the maximum n plus first derivative. And then everything else is going to feel familiar. We're still going to do the n plus first factorial, and then x minus c to the n plus first factorial. Sorry, n plus first power, not factorial. So really, what's new is trying to figure out how do we do this portion. We know how to find the n plus. We know how to get to the first unused term, but how do we get to that unused term, or how do we get to that maximum value? Okay, let me go through one example. Or actually, let me do this. Let me on the next page, I have some things defined, and then we can kind of go back and forth between them because it does feel like a lot. But so let me point some things out. We can continually reference this as we work through these problems. But let me give you guys a moment if you need to finish copying. Everybody good here? So there's a lot of variables here. So I just want to do a quick summary. We can always refer back to this as we work through more problems. But again, the nth degree polynomial or nth degree remainder is going to be the maximum of the n plus first derivative evaluated at z. We don't know what that z is, but we're just going to find the maximum that this can be to kind of create that safe upper bound over n plus 1 factorial times x plus x minus c to the n plus 1. So our n of x, that's the error bound or the approximation between the Taylor polynomial and the function f of x. X is going to be the given value. So in the problem, it'll always tell you what that x value is. C is the center of the function. So the problem will also reference what that center is, unless it says that it's a Maclaurin series. If it's a Maclaurin series, then we just have to know that our C is going to be 0. N is the degree of the polynomial, so that will also be referenced in the problem. And Z is just some unknown x value between C and x. And then we know where the maximum y value of n plus first function lies. So if we want to find the maximum of the n plus first derivative, we just have to figure out, we just have to test f of c and f of x to see which one has the larger value. Whichever has a larger value will be a safe upper bound for that interval. So yeah, so right here, down here, we want to maximize the n plus first derivative on the interval from x to c, or between c and x. The maximum error bound is the worst case scenario for the interval on which our actual approximation can live. Some students have asked in the past, wait, what if the maximum value is not at c or at x? What if the maximum value is somewhere between c and x? If that's the case, then we're not able to find the maximum value of that n plus first derivative. Well, to account for that, College Board or the AP exam they've said that it's always going to be increasing or decreasing. So you're never going to be caught off guard with a maximum value that is neither at c or at x. It's going to be at one of those 2 points. Okay, so to make it a little bit more straightforward from the fact that we don't have as much resource beyond this, they're going to ensure that either c or x will guarantee a safe upper bound. Okay. All right, let's go back to example 1, and we'll kind of go through these problems slowly. This may take a little bit of time, but the idea, the big idea is still there. We're just taking alternating series, error bound, and just adjusting it slightly because of the fact that it's no longer an alternating series. But we can still involve the first unused term to help us find an error bound. Okay, so the fourth degree Maclaurin polynomial, so that tells us something, right? We know our C value is what? C is 0. So I'm going to just start gathering information as I come upon it. It's given by the fourth degree Taylor polynomial. So I know what my n value is. My n is what? N is 4. So I'm just gathering information. If this polynomial is used to approximate cosine of 0.2, guess what that 0.2 is? That's the x, yeah. So okay, what is the Lagrange error bound? So we know that we want to find a safe upper bound between cosine of 0 and cosine of 0.2. But there's something nice about cosine, is that if we look at a cosine graph, like this. What's the largest value that a cosine can hit? Right? 1 and -1, right? So we know, well, the absolute value of -1 is 1. So that's easy. We don't have to worry about, okay, what's larger between 0 and 0.2. We know that sine and cosine have a nice upper bound of 1. So that's just a nice, safe upper bound that we can create. Right. So same thing between sine and cosine. Right. So let's go ahead and fill out everything that we can, and we can fill in some of those additional pieces. So I want to find my fourth degree error bound. So I want to find the fourth degree remainder at 0.2. We know it's going to be less than or equal to the maximum of the n plus first derivative. So in this case, which derivative are we going to be looking at? Fifth, right? Okay, so the fifth derivative evaluated as some z, which we don't know, but it's okay. Over what? Factorial times x minus c. What's our x? 0.2 minus 0. So I'm going to drop that 0 there. Raised to the fifth. Okay, so everything's in front of us. We just have to figure out what to do here. Now, we kind of already know it's going to be 1 and -1, or 1, because we're doing absolute value here. But let's just talk for a moment here. Let's say we want to make our way down to the fifth derivative. Okay, so our function is cosine . Right, ultimately, it may not matter in this case because we know sine and cosine will have a safe upper bound of 1. But let's just go through this process here. So cosine becomes negative sine, followed by negative cosine, followed by sine, followed by cosine, followed by negative sine. So the maximum value that negative sine can be is also 1. So we can replace this whole thing with 1. So 1 over 5 factorial, 0.2 to the fifth. Enter this in our calculator. Okay, we don't have to write all this out. You can leave it in that form. So after, even with a fourth degree Taylor polynomial, we're gaining a really good approximation. Well, partially because we're so close to the center. I mean, we're so close to 0. We know 0 is going to be exact. So 0.2 after 4 degrees is still going to be very, very accurate. Okay. We don't know what the exact error is, but it's okay. All we care about is finding a safe upper bound for our Taylor polynomial. Okay, so over the course of this class, I just want us to kind of get as much practice and as much reps through this, and we're just going to practice with this particular error bound. Okay, let's go to page 43. Use the third degree Taylor polynomial on the interval from 0 to 1 for e to the x centered about x equals 0 to approximate e to the first. What is the error bound of this approximation? Okay, so I'm just going to gather as much information as I can. Third degree Taylor polynomial. I know that my n is 3. Centered at x equals 0. It says x equals 0, but this is really what? This is what value? That's really the c value. So let's just say c equals 0. Which means our x value is what? 1, yeah. Okay, let me build my my remainder formula. So r of n of x, so r of 3 of 1 less than the maximum. Okay, which derivative do I want to use? Fourth derivative over factorial times. You get 1 minus 0. I can drop that. Well, it's not going to make a difference, right? That 1 is just going to be just going away. So we're talking about e to the x here. What's the fourth derivative of e to the x? E to the x. So we want to figure out, okay, fourth derivative is it's just e to the x. Okay, so between 0 and 1, which one is going to be the larger value? E to the 0 or e to the 1? E to the 1. So that's all we need to care about. If we want to find the maximum value, just test your x and c value. Don't have to worry about anything in between. Whatever is larger is going to be your safe upper bound. So that will go in for this. There's our remainder.
So where'd you get for z?
Oh, right here. This is the n plus first derivative. So if this is 3, I got to make out a 4. And this is asking for the fourth derivative of e to the x.
Oh.
So my fourth derivative is that's nice. It's still e to the x. And then if I want to maximize that value, I just have to test which is larger, e to the 0 or e to the 1. E to the 1 is larger, so that's going to be the maximum value. And it's always going to be either between, it's either the one of the endpoints will produce a larger value, or it could be like a sine and cosine where you already know what it is. So it'll be either obvious or you just have to test the two endpoints. Okay, 3 is a little messy. Let me come back to number 3. Let's do a practice. Let's start off with practice. Bottom of page 43. All right, third degree Maclaurin polynomial or sine of x is given. So we recognize this, right? This is Maclaurin series for sine. If this polynomial is used to approximate sine of 0.1, what is the Lagrange error bound for this? Okay, so what do we know? Maclaurin polynomial, so let's just start gathering values for the variables that we're going to need for our remainder formula. Maclaurin means c equals 0. N equals 3, okay. What's my x value? 0.1, yep. So my interval is between 0 and 0.1. Okay, are we okay with the setup so far? So the fourth derivative of sine will bring us back to sine. And what's the maximum value of sine? 1. So that's easy, right? We don't have to do any testing between 0 and 0.1. We can just safely say, okay, for sine and cosine, my max is going to be 1. So that's going to make it easy for us. Yeah.
So you still use 1 even though sine wouldn't reach 1 in the interval?
Yeah, yeah, because it's just a safe value, right? You know, we just want to just have a safe upper bound, and 1 is a nice safe value. Yeah.
Can you use sine of 0.1 as a safe upper bound too? Or sine of 0?
Well, sine of 0 is definitely not going to be as large, right? It wouldn't be wrong, but typically, if it was on the AP exam, they would choose 1 as a safe upper bound. Right. Mm-hmm.
What's the point of P of X being stated?
Yeah, we didn't really need it. But I think there are times when we may be well, they did state it. So it looks like in this case, we didn't really need it. But I'm trying to see if there are problems where we're gonna need the series to help us get to that term. I don't think so. Yeah, I don't really see other problems where they're kind of just stating that information, but we didn't really need it. Okay, let's keep going. We'll just do as many as we can. So we can kind of see as many of these examples. Okay, page 44.
But you do need the series.
I'm sorry?
I think for number 2, you do need the series.
Well, I think the series is just telling us what. Okay. And yeah, also what? Center is what? 0, right? This is basically a Maclaurin series there. That yeah, so this, yeah, you're right. It does give us some information. Our C is 0, and then we know our degree is 4.
Wait, will this formula be given or does it have to be memorized?
Memorized, yeah. Mhm. Oops, sorry. 4th, right? My bad. Yes.
Why would n be 4 if there's 3 terms?
It's 3 terms, but it's a 4th degree polynomial. So that means our n is 4 and then n plus 1 is 5.
Correct.
Yeah. Okay, let's do one more here, number 3.
How do you know like what other X value to test?
You're only testing 0 and 1. Yeah, so you're only testing your center and your X value. That's all you need to test.
Oh.
That unless it's sine and cosine, then you just know it's gonna be either it's always gonna be 1. Right. So if you don't know what the max value is, your max value will be guaranteed to be either at one of the C or X values.
Jake, why is that?
Good, because this is E raised to what power? E is raised to the,
To the X, right?
no, not to the X. It's just E.
Oh.
So to the first.
Oh,
So it's like a understood that, okay, it's E to the,
okay, I see.
yeah, down.
To the first.
So it's hidden, but we know it's E to the first power. Mhm.
If we're looking and evaluating the derivative to see which, if the X or the C is bigger, are we looking at like the magnitude, like if one was more negative, that would be.
Well, we don't have to worry about it because the absolute value will take care of it. But yeah, it'll be the magnitude.
Like when you're comparing the size of the. Like if your X gave you an F6 value of like -3 and your C gave you a -1, you would take the -3.
Mm.
I think your absolute value is.
Yeah, no, you're right. Let me yeah, let me get back to you on that. All the values that I've seen with X and Z have been positive, but that's a good question. Let me get back to you on that.
On the test, you want us to round it or keep it exact?
3 decimal places
Okay.
is, yeah, I know I'm doing more than that, but yeah, on the AP exam, I would say 3 decimal places should be sufficient. Okay, so for homework, you guys will finish up to the page 53. But if you guys can skip page 48, I think I want to do this with you together. So this is a FRQ problem involving Maclaurin series, but I think I want to just be able to spend time going through this with you. So you can skip page 48, but you can do the rest. Okay. Anybody know what the significance of today's lesson is?
That's Calc BC topic.
Yeah, this is our last lesson. Okay, so it's nice. We have a luxury of 2 full months to review. But tomorrow we'll finish this last problem up. I'll give you guys a test review. So we'll start test review tomorrow. We'll do test review Monday, Tuesday, and Wednesday. Your test will be next Thursday. I'll have help sessions over the course of next week. And then I'll give you guys a calendar after next Thursday. Can I have, my various calendars and review all set up? Yeah.
Is the test just on the second half of the meeting?
Yes, but we do need to know that conversion
No.
just within the context of this. Yeah. Yeah. Just basically, we still know, how to do harmonic series, alternating series, that's all that stuff. But essentially, yeah, just 5.5 to 5. Oh, sorry, 10.5 to 10. All right, come get your votes.
They might have used, then
Barely.